Hi, this is Sonia Doucette. In this problem, I'll show you how to calculate the equilibrium constant from the delta G naught value for a reaction in order to use the K value, or the equilibrium constant, to determine the general composition of the reaction mixture. And by general composition, I mean, is the reaction mostly products at equilibrium, mostly reactants at equilibrium, or are there appreciable amounts of both product and reactant at equilibrium? For this specific problem, you're told that delta G naught for the dissolution of sodium sulfate is 25 degrees Celsius, or at 25 degrees Celsius is 1.05 kilojoules per mole. You're asked to calculate the equilibrium constant using this information to determine the general composition of this reaction mixture. So the important relationship to know to solve this type of problem is that delta G naught is equal to negative RT ln K. So R is the ideal gas constant, T is the temperature in kelvins, and K is the equilibrium constant. And delta G naught is the free energy of reaction under standard conditions. So you're given the delta G naught value, you know your temperature is 25 degrees Celsius, and you know the ideal gas constant. So what you really want to do here is solve for K. So rearranging the equation in terms of K, you have the natural log of K being equal to delta G naught divided by negative R times T. In order to get K by itself, you take the natural log, or you raise both sides to the E. So E to the ln K equals E to the negative delta G naught divided by RT. And that's going to give you K equals E to the negative delta G naught RT. So all you need to do is plug in the terms that you know here. But before you do that, you need to make sure of two things. First, you have to make sure that your temperature is in kelvins. So here you have 25 degrees Celsius. When you convert that to kelvins by adding 273.15, you get a temperature of 298.15 kelvins. And then the other thing you need to do is convert your R value. So your ideal gas constant is usually given as 8.314 joules per Kelvin mole, but that's in joules, and your delta G naught value is in kilojoules. So if you convert your R value to kilojoules by dividing by 1,000, you will get a value of 0.008314 kilojoules per Kelvin mole. So now you have the values that you can use to substitute into this equation. So you can say K is equal to E to the negative 1.05, and that's in kilojoules per mole. And you're going to divide that by 0.008315, which is your ideal gas constant in kilojoules per Kelvin mole, multiplied by the temperature of Kelvin in kelvins, which is 298.15. So if you do the math here, what you're going to end up with is a K value of 6.55 times 10 to the negative 1. So some rules of thumb here. If you have a K value of greater than 1, then you know that your equilibrium mixture is mainly consisting of products, because your K value is large. If you have a K value of less than 1, you know that your equilibrium mixture is mainly reactants. And if you have a K value equal to 1, you know that your equilibrium mixture has appreciable amounts of products and reactants. So in this case, the K value is less than 1. It's 6.55 times 10 to the negative 1. So that means that your reaction mixture at equilibrium will be mainly reactants. So you found your K value using delta G naught, and then use that K value to determine the general composition of your reaction mixture. So you're done.